So let me start by the question, so what is a random graph? So the model that people use is, the standard model is due to Erdös and Rényi. So the Erdös and Rényi model of a random graph, which is often denoted GNP. So it's a probability space where it consists of graphs of n vertices, and each pair of vertices you just define to be, you declare them to be connected by an edge with probability p. So is the probability space of graphs with n vertices where each edge, well, each pair of vertices span an edge with probability p. You know, where p is some fixed function, maybe I'll usually write p, but really it's p of n, and it's some fixed map from the natural numbers to 0, 1. And actually usually I'll say that it's inside 0 and inside 1. So that's what a random graph is. So the simple case to think about is where this is a constant function, and like the constant function 1/2 means, you know, the random graph is in GNP if you fix n vertices, and then in GN 1/2 if you fix n vertices, and then for each pair of vertices you flip a coin. So you do this n choose 2 times, and you put in all those corresponding edges. So that gives you some graph. And you can do this for any n, and really you can do it for any probability function, for any function from n to 0, 1. Okay, so sort of, and what you want to think about is what happens as n increases. So given any property of graphs, so any graph theoretic property, you know, you can ask the question, how often does the graph in GNP satisfy that property as n goes to infinity? So you sort of fix some p, you fix some probability function, and you fix some graph theoretic property, and then you ask sort of what the asymptotics are of satisfying that property. So when the probability that a graph in GNP, so that GNP satisfies p limits to 1 as n goes to infinity, we say GNP satisfies this asymptotically almost surely. So GNP has property p asymptotically almost surely. Okay, so let me now say what the kind of the most classical theorem in the field is. So this model was introduced by Erdös and Rényi in 1960, and actually I'm lying there slightly. So there's several different models of random graphs. All of which, there's sort of 3 main models, all of which are called the Erdös-Rényi model. This model was actually introduced by Gilbert, and it wasn't the one they originally used, but all the different models are equivalent, and this is the one that's sort of most common now, and people often just refer to this model as the Erdös-Rényi model. So if you look it up, you may see something slightly different, but there's kind of 3 different models, and they're all more or less equivalent. So, all right, so here's the theorem of Erdös-Rényi from 1960, and since then this has become, the study of random graphs has become a major field in combinatorics. It's sort of a big part of combinatorics, but this is the theorem that got everything started, and it was a study of of behavior of these random graphs. So what they proved is that if P, so P of n, is bigger than or equal to 1 plus epsilon log n over n, for some epsilon greater than 0, then GNP, so a graph in GNP, is asymptotically almost surely connected. Okay, so you kind of build this random graph, and anytime you take a probability function that's bigger than this, then the graph that you construct is going to be connected. And similarly, if P of n is less than or equal to 1 minus epsilon log n over n, then GNP is asymptotically almost surely disconnected. Okay, so this has become known as a sharp threshold theorem. It says that there's some function, really log n over n is the function to think about, and as soon as you're a little bit bigger than that, then asymptotically almost surely you're connected, and as soon as you're less than that, then asymptotically almost surely the graph you build is not connected. And if we think about the kind of simple case I said before, well, the constant function p is bigger than log n over n, so that sort of random graph will be connected. Okay, so this is the sort of model we want to have in mind, and we want to try and build theorems about groups that are similar to this. Okay, so let me now introduce right-angled Coxeter groups, which is the family of groups that I want to think about. And I should say, maybe this is a good place to say on this board that will stay here, but no longer says when dinner is. So this will all be joint work with 3 people. So one is Victor Falgas-Ravry. That's one person. One is Mark Hagen, who's here. And the other is Timothy Susse. Okay. All right, so what's the definition of a right-angled Coxeter group? So these are related to right-angled Artin groups, which we heard about the other day. And they're also groups that have been studied for a long time and provide a lot of interesting examples. So let's fix, for the definition, gamma to be a simplicial graph. So, and always I'll have the, whenever I say graph, I mean finite simplicial graph. So then the right-angled Coxeter group, RACG, presented by gamma is defined this way. Okay, so I'll just tell you explicitly what the presentation is. So for every vertex in gamma, we add a generator. And unlike this is where it differs from a right-angled Artin group, unlike in a right-angled Artin group where you just put in an infinite order generator, really there's kind of a relation here too, because my generators are all going to be order 2. So add an order 2 generator. Okay, so I put in an element of z mod 2z for each vertex, and then, so for each edge in gamma, we declare the associated generators to commute. So this is, well, okay, so edges here mean commutation. It's the opposite of what the convention was yesterday for writing Artin groups, but that was also the opposite convention people often use for Artin groups. So this is the standard convention. Okay. All right. So these are the right-angled Coxeter groups. So let's go through and just give a couple basic examples. So the simplest example maybe is you have n vertices that are not connected by an edge, and that gives you a so n vertices gives you the group you get. So this is gamma. So over here is going to be, let me give a name to it. So if I call this graph gamma, then I'll call the right-angled Coxeter group W gamma. So over here will be W gamma. So this is just the free product of n copies of Z mod 2Z. Okay. On the other hand, if we take the n simplex, then we get a copy of Z mod 2Z raised to the nth power. Okay, so here you get a finite group in the case of an n simplex. It turns out those are the only finite groups that you get from right-angled Coxeter groups, but you can get finite groups. So the next example to think about is a square. So a pair of vertices that are disjoint generate a copy of the infinite dihedral group. So really I want to think about this as consisting of kind of this orange group, which is an infinite dihedral group, and the purple group, which is an infinite dihedral group, and then these edges, right? Every orange vertex commutes with every purple vertex. So this generates a direct product of two infinite dihedral groups. So let me just say this is a group which is virtually Z squared. Okay, so this is going to be an important example for us. So that's a good one to have in mind. And just one more example to show some of the variety is that if I take the n, so I take an n-gon for n greater than or equal to 5, well, so then the group I get there, it turns out you can realize this in the hyperbolic plane by taking a right-angled n-gon. And so you take this right-angled n-gon, you extend each of those geodesic segments to kind of bi-infinite geodesics, and now you've got these a bunch of lines in the hyperbolic plane, and then you can think about reflections in those, and you can look at the full group of reflections you generate, and you get a tiling of the hyperbolic plane, and that shows you that this group is virtually a surface group. So this is virtually a surface group. Okay, so unlike in the case of right-angled Artin groups, you get some hyperbolic groups that appear among the class of right-angled Coxeter groups. So there's some behavior already that doesn't show up in the case of right-angled Artin groups. But this class is very big, and through the theorems of like Agel and Wise, you get many interesting subgroups, right? Through their theorem, you get that every hyperbolic three-manifold group is a subgroup of some right-angled Coxeter group. So it's a really large class of interesting groups, but even though they have this kind of very nice, simple presentation. So what I want to do next is show that, so these were just some examples of the graphs. What I want to show is that there's actually lots of interesting graph theoretic properties which get encoded, so lots of interesting group theoretic properties that are encoded in graph theoretic properties. And so there's lots of places where you can go back and forth between the group theory and the graph theory. All right, so maybe I'll put this on a new board. Oh. Let's see. Actually, maybe I can just fit it here. I'll put it here. No. All right. Okay. All right, so the first graph theory, so what I want to do is sort of have some properties of graphs over here and properties of groups over here and produce the relation between them. So, and this will be nice because then anytime we have a purely graph theoretic property which encodes a group theoretic property, then we can go back to the Erdös and Rényi model and ask, what is the what sort of does the random right-angled Coxeter group satisfy this? Where the random right-angled Coxeter group is, you just generate a random graph, and then you build the right-angled Coxeter group with that graph. So the first maybe graph property is a clique. So is a complete graph on n vertices, or I guess is a simplex maybe is the word I was using. Either one's fine. So it's a simplex, and as I already said, the corresponding group you get, now you've got n vertices and they all commute with each other, so each one was finite order, so you get a finite group. So on the group side, these correspond to finite groups. So the group is finite. Okay, so there's sort of there's a purely group theoretic property. All right, so the next one is a little more interesting. What if the graph contains a separating clique or simplex? Okay, so there's maybe some vertex which disconnects the graph, or there's some, there's some n-gon, some tetrahedron, which when you remove that, it separates the graph. What does that correspond to? Well, there's a theorem of Mike McCulloch that says that this graph theoretic property is equivalent to your graph splitting over a finite group. So, so the right-angled Artin group splits over a finite group. Right, so those are the obvious splittings, and his theorem is that any splitting that you get in a right-angled Coxeter group is one of these obvious, any splitting over a finite group is one of these obvious splittings. So he calls these visual splittings. So this is kind of another interesting property that relates graphs and groups. All right, the next property I want to think about is that the graph is a join. Which for me, I usually denote gamma is equal to, say, gamma 1, I'll put a star, gamma 2. Okay, well remember for us, so a join means we take every vertex on one side and we attach that to every vertex on the other side. In other words, we're making every element, if we think about the corresponding group, every element in every one of the generators over here will commute with every one of the generators. So joins correspond to direct products. So W gamma splits as a direct product. Right, so W gamma is equal to W gamma 1, direct product, W gamma 2. All right, so that gives us another one. So the third one maybe to think about is containing squares. So the graph contains an induced square. Okay, so by induced square I mean that right, you draw this, well, so if you draw a square, then it's an induced square if none of the diagonals are secretly there inside the graph. So remember, a square, as I said up there, is a group that's virtually z squared. Okay, so a square in the graph corresponds to the group containing a virtual z squared. So that's obviously an obstruction to being a hyperbolic group. And the theorem of Mousson is that that's the only obstruction to being a hyperbolic group. So in fact, containing an induced square happens if and only if W gamma is not delta hyperbolic. Okay, so it gives you a simple criterion for recognizing hyperbolicity, and maybe this is a good point to go back to the Erdös and Rényi model and think about how often this happens. So when do you get induced squares? Well, so an induced square, let's just draw it even though we all know what it looks like, right? Induced square consists of 4 points, okay? So there will be n, choose 4 ways that we can pick those 4 points, and then what do we need to have? We need to satisfy that these pair are connected by an edge, and these pair are connected by an edge, and these pair and these pair. So there's p to the 4th ways, there's p to the 4th configurations that have to happen, and then we need to have that this is a non-edge, and this is a non-edge. So it's p to the 4th times 1 minus p squared. Okay, so that's the probability of having some square in your space. And now n choose 4 is approximately n squared. Is approximately n to the 4th. So the probability of containing a square is approximately, so the probability that there exists a square is approximately n to the 4th, p to the 4th. There's a 1 minus p term also, but when p is small, So that's close to 1, and that goes away, so it's approximately n to the 4th, p to the 4th. So you can see that this happens whenever p is bigger than 1 over n. So the probability that you contain a square, so you're likely to contain a square when p is bigger than 1 over n. So, and in fact, you can show that, so in fact, one of Erdös and Rényi's, one of the other theorems in this original paper from 1960 was that, they proved that, so this is sort of a probabilistic statement, and then you need to ensure that this happens, well, so you want to show that this works asymptotically almost surely, and then this tells you that the probability of having an induced square is bigger than 1 over n. So the likelihood of not being hyperbolic is very high. So even before you get to even before you get to a point where you're connected, right? So the random graph isn't connected until probability log n over n. Even lower than that, when you're still splitting as a free product, then you're likely to contain a square. So there's lots of so most random Coxeter groups will be not hyperbolic as long as we take a range bigger than 1 over n. Okay, so kind of the moral of this is that most random Coxeter groups are not delta hyperbolic. So where does that leave us? Well, there's one more property I want to talk about, which is relative hyperbolicity. So the last bullet point. Maybe I can even fit it here if I put this up a little more. So the last bullet point is that there exists a class of groups, which I'll call tau, and this class of class of graphs, tau, which has the property that gamma is in tau if and only if, or maybe I'll say first what it means for gamma to not be in tau. Gamma is not in tau if and only if W gamma is relatively hyperbolic. Okay, so relative hyperbolicity is sort of a generalization of hyperbolicity where you allow there to be non-hyperbolic behaviors, but you require that they be sort of isolated from each other. So one simple example is if you have a free product, then free products will be relatively hyperbolic relative to their free factors, and there's obviously more complicated relatively hyperbolic groups also that don't split as free products. So we have this class of graphs where if you're not in that class, then you're relatively hyperbolic, and we also know something about what's in that class. So gamma is in that class if and only if W gamma has polynomial divergence. Okay, so this bullet point here is a theorem of myself and Mark Hagen and Alessandro Sisto, and it's what motivated the talk that I want to give, the results that I'm gonna focus on today. So there's this class of graphs, and if you're in that class, then you have polynomial divergence, which is something that I want to define, and that I'll spend a little bit of time on now. And if you're not in that class, then you're relatively hyperbolic. And the class of relatively hyperbolic groups also contains the class of hyperbolic groups. But if you want to think about the ones that don't, then really I like to think about this as a trichotomy. So there's a trichotomy here, which is that W gamma is either, so any right-angled Coxeter group is either hyperbolic or relatively hyperbolic in a non-trivial way, or polynomial divergence, or has polynomial divergence. And the reason I want to state this as a trichotomy and think about it in this way is that given given this model of random graphs, the question that we immediately think then is, well, what's the behavior of the random graph? So if we take a random graph and then we build a right-angled Coxeter group, is that going to give us something that's hyperbolic, or is it going to be kind of non-trivially relatively hyperbolic, or is it going to have polynomial divergence? Right? I mean, the Gromov random group is hyperbolic. So our naive expectation, should have been that the right-angled Coxeter groups we're going to build in a random way are going to all be hyperbolic. But I've already explained that that's not the case, because for random graphs, as long as you take sort of an interesting probability, one that's bigger than 1 over n, you're getting non-hyperbolicity behavior. So already you're forcing it to either be relatively hyperbolic or polynomial divergence. And then the question is, which behavior are we going to get? And maybe I'll just mention without writing down, there's a theorem that Mark Hagen and Alessandro Sisto and I proved was that we proved, if you think about the simplest version of random graphs, which is gn 1/2, so you just flip a coin, and it's an even coin, and it tells you whether you put an edge or not. That builds some graph for you. What's the behavior of that graph? Is that graph going to be, well, we know it's not going to be hyperbolic, but by the Erdös and Rényi theorem, is it going to be relatively hyperbolic, or is it going to have polynomial divergence? And the theorem that we proved was it was going to have polynomial divergence, but we proved it in a non-constructive way that didn't tell us at all. It didn't give us any bounds about the divergence. And so what I want to do today is, after I define divergence, I want to tell you what the divergence is in that case. And in the meantime, you can think about that. You can try and form a conjecture of what's going to happen. It has polynomial divergence. Maybe as n goes to infinity, that divergence sort of blows up to infinity, and so it kind of gets closer and closer to something sort of hyperbolic in the limit. Maybe it stays uniformly bounded, but sort of you don't know what it is, or maybe you can get some concrete control over it. So those are kind of the three things that might happen given our theorem, and I'll tell you which one it is. Okay, so having said that, let me now move on to divergence. So I didn't say that, but that's a fact. So right, if you're right, so contains a separating simplex. So if the I count the empty set as a simplex, and so if you split over the empty set, then you're splitting over the trivial group. Okay. All right. So what is divergence? So let me draw the motivating picture is the following. So you have so divergence can be defined in a much more general setting than in groups. You can define it really for any geodesic metric space, but really, we'll be thinking about right-angled Coxeter groups, or finitely generated groups, but really we could define this much more generally. And then, so the idea is you now have some bi-infinite geodesic in your space, and if you picked a point on that geodesic, then you could imagine taking a ball of radius n around that point, deleting that out from your space, and asking how far apart are these 2 points in the complement of that ball. Okay, so what's the shortest path in the complement of this blue ball connecting them? So right, if I just pick 2 points on the geodesic and I said how far apart they are, then the answer is obvious, right? You just go along the geodesic. But now I've removed this kind of ball around the geodesic, and I want to know how long that green path is. So this is what the notion of divergence captures. Maybe a more precise way to say it is that the divergence of the space X. So it's going to be a map. So really, it's going to be a function. It's going to be a map from the natural numbers to the to the positive reals union infinity. Maybe there's no way to connect them, in which case I'll just say it's infinite. But for every number n, what we want to do is we want to look at pairs of points, which I'll say call A and B. Okay, and to each point A and B, I want to look at the max, or really I should maybe say the soup over triples A, B, and C, where A and B are what I just said. So A and B, where the distance between A and B is, say, n. Okay, so the distance between these 2 points is n, and C, so the distance between C and, okay, I see, and C is arbitrary. So you look over all possible C, and you measure the distance. You now measure the distance in X minus a ball. So I'm going to want to measure the distance between A and B in X minus the ball of some radius, which I'll tell you in a second, around C. And the radius is, what I want to do is I look at, here's my point C sitting in the middle, or sitting somewhere, okay? I look at the distance between C and A and C and B, and I look at the smallest of those. So maybe this is R here, okay? I look at the distance between C and the set AB, and then I'm going to multiply that times 1/2. So I'm going to remove some fixed ball of radius. So the radius of this ball is going to be the distance between the set A comma B and the point C times 1/2. Okay, so this is sort of the model. This model picture was C was right in the middle, and I removed the ball of radius of just radius, n over 2 in this picture. But more generally, you can allow C to vary, and this gives you a notion of divergence. I take the soup over all possible triples. Okay, so for each one of these, you look at so for every point, for every pair of AB at distance B, at distance n, and every point C kind of between them, you avoid this ball, and you look at all those configurations, and then you take, for each one, you look at the shortest path, and you look at the worst way you can do that, and that's the divergence function. It tells you sort of what's the worst configuration of points that I can have where it's very hard to avoid the ball between them. And it turns out that this function, so this version of the divergence was introduced by Drutu, Moses, and Sapir, and this version is a quasi-isometry invariant. So you can associate, the growth rate of this is a quasi-isometry invariant. So to any group, you can associate this function, and that depends on the generating set. You might get slightly different functions as you vary the generating set, but the growth rate of that will be a quasi-isometry invariant. So that's what Drutu, Moses, and Sapir proved. So you can ask the question, does my group have quadratic divergence? Does it have cubic divergence? Does it have polynomial versus exponential? Sort of what's the growth rate? And that's a quasi-isometry invariant of the group. So having said that, let's now give some examples. Okay, so there's lots of examples with interesting divergence. Let me start with kind of the simplest examples. The simplest ones are linear divergence. So z to the n has linear divergence. Anytime you have, in fact, more generally, anytime you have a direct product of infinite groups. So direct products have linear divergence. So Drutu and Sapir proved that groups that satisfy a law okay, so nilpotent groups, solvable groups, Burnside groups, etc. Those groups all have linear divergence. A family of groups that I like are ciphered fiber, pi 1 of a ciphered fibered space. So this is a class of 3 manifold groups. These ones all have linear divergence. So there's lots of interesting groups, and the list goes on. There's lots of interesting groups with linear divergence. So what comes next? Well, the next polynomial to think about is quadratic. So actually, it was an open question for a long time if there were things between linear and exponential. The first example was given was one by Gersten, where he proved that pi 1 of a non-geometric graph manifold has quadratic divergence. So, if you know about three manifolds, this is an important class of three manifolds, and those all have quadratic divergence. If you don't, then let's just talk about a few other examples. So mapping class groups. So except for in the kind of degenerate case, except for in the low complexity cases where you get a group which is hyperbolic, otherwise you have quadratic divergence. So that was a theorem that was proven by me quite a while ago in my thesis. So mapping class groups all have quadratic divergence. Right-angled Artin groups. So Ruth Charney and I proved that right-angled Artin groups all have quadratic divergence. So, and actually there was an independent proof of that was given by Abrams, Brady, Donnie, Duchin, and Young. So there's proof of that. In fact, there's now a proof using a recent theorem of Charney and Paris that all Artin groups actually have all Artin groups either have actually, so for RAGs also, for both these classes, all either have linear growth or quadratic. And you can kind of classify exactly which ones have linear divergence and the rest of them have quadratic. So maybe they should say at most quadratic, but so anyways, there's lattices and Lie groups, there's lots of things. So this list also is very long, goes on. It contains lots of examples that are studied heavily by geometric group theorists. Maybe I'll leave a gap for a second and let's go over here to exponential. Yes? When they're not direct products, yeah, right. Okay. So for exponential, this includes hyperbolic groups, and it includes relatively hyperbolic groups. And let me leave it at that. But there's other examples, and for a long time, it wasn't known whether there was anything between quadratic and exponential. So, Gromov had asked whether there were things between linear and exponential, and after a few years, Gersten proved that there were, and then it was asked whether there were things between quadratic and exponential, and that was unknown for a long time. But it turns out that's now known also. So there was maybe I'll just say examples. So there were examples that were constructed by Cornelia Jutu and I, and also Natasha Makura constructed examples that had polynomial divergence and examples in every degree. But what's relevant for this talk actually is that there's actually a really nice family of examples, which is so Pahlavi, Donnie, and Ann Thomas, they proved that there exists right-angled Coxeter groups that have polynomial divergence, and you can get them in every degree. So they kind of constructed some explicit family where there was one in each degree. So you can get lots. So there's some interesting polynomial divergence examples, and then by my theorem with Hagen and Susse, which was proven after this, but sort of motivated by their theorem. In fact, there's a bunch of them. So anyone that's not relatively hyperbolic or hyperbolic has polynomial divergence, although exactly how many was sort of open for a while. So let me now put up, let me now put up a theorem, one of the main theorems. So this is, so our theorem is, or one of our statements of our theorem is the following. So if you have some probability function, so we're going back to the Erdös and Rényi model, is bigger than or equal to 5 times the square root of log n over n, and gamma is in so let me say it like this. Then asymptotically almost surely any graph, any gamma in GNP has W sub gamma with quadratic divergence. Okay, so we showed, so remember I'd said that in the constant probability case, I had this older theorem with Hagen and Susse, where we showed that in Gn 1/2, that they always had some polynomial divergence. Well, any constant probability is bigger than, grows faster than 5 times the square root of log n over n. So any constant probability has in fact quadratic divergence. So unlike what we thought we might expect, which is that the divergence sort of blows up as n gets bigger, in fact, these things all have quadratic divergence. So one nice aspect of this is that if you go back to if you go back to thinking about the Gromov theory of random graphs, or random groups, Gromov random groups are always hyperbolic. And while there's lots of nice things about hyperbolic groups, certainly those aren't ones on this list. They're not sort of they're not, well, for a long time that was what most geometric group theorists were studying, but that's no longer the case. And so if we go back to all our sort of, some of the most favorite examples studied by people in this room of quadratic divergence, somehow this model of random groups, where you think about a random right angled Coxeter group, actually produces things that are what we often see in the everyday world as geometric group theorists, things with quadratic divergence. So this is sort of I think of this as an argument in favor of thinking a lot more about this model of random right angled Coxeter groups and trying to kind of develop a theory there. All right, and actually let me just, as long as I have this on the board, let me just advertise that there's a group that's conspicuously absent from this, which is out of n. And so there's a number of experts in this room on out of n. We just heard talks that were relevant to that. But it's still unknown what exactly their divergence is. So there's a theorem of myself with Cornelia Drutu and Lee Mosier, where we prove that their divergence is at most quadratic. There's a theorem that gets you close to knowing what the divergence is, by Algum Kafir, and that was independently proven by Hammenstadt, where they prove that outer space has quadratic divergence. So they don't prove out of n has quadratic divergence, but they prove outer space has actually at least quadratic divergence. Their proof then tells you something about Fn, which is that it tells you that it's superlinear. So it's known that out of n lives somewhere in here. So it's bounded away from here, and it's maybe quadratic. I mean, I've been promoting this question for a long time of proving that it's quadratic. That's what I'd conjecture it is. But it's not known to this day what it is. And so I think that's a good question that someone ought to focus on. There's either one of the experts in out of n that's in the room or one of the many graduate students that are here. Okay. So what did you say? Yeah, and at least 3, right. If n is equal to 2, then you're hyperbolic. So yeah, just like with the mapping class group, I'm throwing away the kind of degenerate case that people do know. Okay, so let me say a few things now about this theorem with this theorem at the end and how it's done. So let's put this up. Okay, so the first step in trying to prove a theorem like this is to understand what's the graph theory that gives you quadratic divergence. So we have implicit, I should say implicit in that last bullet point that there's something that tells you polynomial divergence is we actually have an explicit class of groups. I mean, we can explicitly tell you that a group has polynomial divergence, but showing which ones are polynomial at which degree remains tricky. So, but it turns out that for quadratic, there's a class of graphs which at least we know are all quadratic, and presumably that class is exactly the class of quadratic groups with right angled Coxeter groups with quadratic divergence, although that's still unknown. So, the class of graphs that are relevant are those that are constructed from squares. And let's see, I was going to tell you the exact definition, but just for the sake of time, let me just tell you kind of what the rough idea is. So let me show you the motivating, well, one of the main motivating examples, and then this gives you sort of an idea of what the definition is. Well, so the idea is that it's constructed from squares. What does it mean to be constructed from squares? It means that you can find some particular square inside your graph. It may not work for every square in your graph, but there's some induced square in your graph that has the property that if you start from that square, and then you fix 3 of the vertices in that square, and then you kind of flip where the last vertex is. So maybe I'll fix these 3 vertices and get rid of this vertex and replace it by some other vertex. Then I can do that, and I can flip from one induced square to another induced square. And I can keep doing that in such a way that I fill out the whole graph. So I start from some fixed square, and from that one square, by flipping along these pairs of edges, I can replace what the third vertex is, and I can do that in such a way that I reach. So I flipped here to get this square, and then maybe I flipped along this edge to get down to this square, which is here, which is also an induced square. And so by kind of a sequence of flips, you can build out the whole graph. You can build out all the vertices of the graph. You don't need to build out all the edges of the graph, but you can build out all the vertices in this way. So those graphs are constructed from squares. And we need to allow a slight generalization of that too, which is obviously if you take a direct product of a group with quadratic divergence so if you take a direct product of a group with quadratic divergence with a finite group, you're going to still get quadratic divergence because I said it was a quasi-isometry. So from a graph theoretic point of view, you need to be able to take one of these graphs and then take a join with a clique. And so inside this class of constructed from squares graphs, you also put graphs that may not have this property but have a subgraph with this property, and the whole graph is a join of that graph with the finite graph. So those are the ones that are constructed from squares. And then there's a theorem of Donny and Thomas where they proved the following thing. They proved that we call these CFS graphs. And then, so if gamma is in CFS and gamma is not a join, right? Because ones that are join will have linear divergence because they'll be direct products. If gamma is in CFS and is not a join and is triangle free, so if there's no triangles in your graph, then this class of gamma, this happens if and only if. So among this, so maybe I should say it like this, sorry. If gamma is not a join and is triangle free, then gamma is in CFS if and only if W gamma has quadratic divergence. Okay, so this tells you a lot of graphs that have quadratic divergence. It gives you a complete classification among those that are triangle free. But the triangle freeness is a problem because for the random graph, you get very large cliques. Okay, so you get lots of triangles in an Erdös and Rényi random graph when the probability, in fact, as soon as the probability is bigger than 1/n, you're going to get lots of triangles. So there's this generalization of this following from theorems of myself with Hagen and Sisto, where we showed that if you can get rid of the triangle free hypothesis, but you don't get an if and only if, or we don't know that you get an if and only if. So if we get rid of the triangle free hypothesis, we can still prove that anything in this class has quadratic divergence. And that's the criterion that we use in order to try to show this theorem. And so let me just put up as the last theorem BFHS. Let me word it like this. So suppose Pn is bounded away from 1. Okay, so the probability goes to 1, then you're gonna in the limit get a complete graph, and that'll have linear divergence. Actually, so there's a bound away from 1 that's implicit in that theorem too, but I made it explicit here for some reason. Bounded away from 1, and let epsilon be greater than 0. Okay, so let gamma be in GNP. Actually, do I want to even say this? Let's say it like this. If Pn is bigger than or equal to n to the minus 1/2 plus epsilon, then asymptotically almost surely gamma in GNP is in CFS. Okay, so in fact we have a strengthening of that, which is that explicit bound there. That's our function, which gives you this. So we have an explicit bound that gives you that you're in CFS, and if, on the other hand, if P of n is less than or equal to n to the minus 1/2 minus epsilon, then asymptotically almost surely gamma in GNP is not in CFS. Okay, so this is kind of a version of a sharp threshold theorem for graphs, and this is what we use to know exactly when you get quadratic divergence. And there's other versions of this that come into play where we kind of introduce some other new graph theoretic criterions and prove sharp thresholds for them. But now I'm over time, so I'll stop. Yeah, that's a good question. So it turns out that if you're willing to leave the world of finally presented groups, then Osen, Olshansky, and Sapir know how to construct groups with kind of any divergence function, or they can construct lots of bad ones. Within the world of finally generated groups, it's not really known what happens. Like within the world of finally presented groups, for instance, it's not even known whether there exist groups that are between linear and quadratic divergence. That's another interesting question. I mean, it's really not known. And within the class of Rényi-Coxeter groups, that's even not known whether you can get, it's known that you don't get anything between linear and quadratic, but between quadratic and cubic, it's open whether you can get divergences in that range. I think not, but amongst all finally presented groups, it's certainly unclear. So what it boils down, well. So one of the big steps, which I was hoping to get to, but I didn't quite get there, is there's sort of an intermediate property that we think about, which we call being an augmented suspension. So the idea is that Mark was hoping I'd get to talk about UFOs. So these are what we call UFOs. So a suspension is you have two vertices and you have some graph in the middle, which you don't know exactly what it looks like, but every vertex on the top is connected to everything on the bottom. Okay, so this is a suspension, and suspensions you see have are direct products, right? So if there's no edge between the top and the bottom, so it's virtually z cross some graph. So that's something that has linear divergence. And so what you want to do to prove something has quadratic divergence is take a bunch of things that have linear divergence and start to chain them together in such a way that you have another thing of linear divergence and it intersects this along some infinite line. And it turns out that using a result of myself with Drutu and Mosier, we showed that if you kind of chain together things of linear divergence, then you have at most quadratic divergence. And so what we do in our paper is we study, so this is a suspension, augmented suspension, is there's some subgraph that looks like a suspension, and every vertex that's not in there is connected by at least a pair of edges to a pair of vertices in here that are not connected by an edge. So every vertex not in this suspension is connected by at least two edges to some non-clique inside here. And we have a sharp threshold theorem for knowing you're in augmented suspension. So it turns out that property occurs exactly when you have when you have P of n bigger than or less than the square root of sorry, not the square root, the cube root of 1 over n to the minus 1/3. So that gives you sort of log n over n, that power raised to the minus 1/3. That raised to the 1/3. So we get sort of a sharp threshold for having this property, and that sort of then gets promoted to proving the more general CFS. And you can show, actually, I mean, the thing that's implicit in this picture is that the advantage of this, when this middle part is not a clique, then that means that there's a pair of vertices that are not connected by an edge. And since the top and bottom are not connected by an edge, you now get the square. You get the square that I was talking about. So you kind of, the CFS property is implied by this one. So this is sort of a weaker property, but it's sort of used then to, it's used to then show that lots of groups have quadratic divergence, that lots of groups are in CFS, and then we kind of push that down farther to get to this bound that we have there. Okay.
And what if a graph is can be decomposed as a disjoint union of joints which themselves, whose components are disjoint unions, etc.
Yeah. So that in a sense, that's sort of what that's one of the things that's kind of encoded in this property is that you know. This is some form of an inductive property like that, which is linear divergence is encoded by being a join. And CFS is really equivalent. There's an equivalent formulation of CFS where you're not a join, but there's a collection of joins inside your graph, which you can think of as these augmented suspensions. And there's a collection of these joins, and together those cover the whole graph, and they intersect in some way. So this is kind of this is one version of the sort of property that you're talking about. And yeah, if you have particular versions in mind that right. Yeah, so if you have a particular version of that you're interested in, then we should think about that, and I'm happy to talk about it with you. And if in general, I don't know if that's been known a lot. I mean, there's very few threshold theorems in graph theory, even though studying random graphs is sort of a big thing. Really, the main threshold that people know is people know what happens for connectivity, and people know local properties. Like you know that there exists a subgraph of a certain form, which is small. What makes our kind of property, I think, particularly interesting is that it's a global property. This is, we're telling you something about sort of how the whole graph behaves, and that's sort of a new type of, even though connectivity seems like a global property, the way that it's proven is via sort of a local property. It has to do with isolated vertices, and so ours has a little bit more of a global nature, so it's a new type of notion. Yeah. That's right. So all those global properties, though, they come from local properties. So I mean, for instance, being connected is a global property, but it's equivalent to not having isolated vertices. So there's sort of a local obstruction to the global property. Okay. Okay, great. Yeah, sorry. Yeah, when I got to that point, I realized I was late on time, so I left out some examples. But yeah, that's a good. Thank you for pointing out that example.